We're going to talk more about Jupyter, and we're also going to learn a little bit about Ascent. So I'll tell you why in a second, but I mentioned that I work on Visit. I also work on Ascent, which is this in situ visualization analysis library. And the reason why we're talking about Ascent with Jupyter is Ascent was not meant to be a GUI tool, right? It was not meant to be a tool like Visit that has all of this stuff. However, one of the things that people fear most about in situ visualization tools is the not being able to do things interactively. You know, they really want to be able to set things up, and they really want to be able to iterate on things. So we decided when we were teaching people how to use Ascent, and also to produce some tools that would help some of these workflows to use Jupyter for that. And it comes in a couple different, I guess, flavors. What I'm going to be showing you today is the most basic use case of using Ascent directly through Python in Jupyter. And I'll talk a little bit more about some of the fancier things, but some of them are magic, and they probably won't help you understand or learn. But I will share a little bit of that, right? So the plan is, let me go ahead and start this up. Yeah, so the plan is I'm going to talk a little bit about Ascent, probably not 10 minutes, probably shorter than that. And then I've fired up 90 different cloud servers, and if it all works in a few minutes, then you all have your own Jupyter server, and I'll show you how to do all that. All right, so I talked through this a little bit, but I want to point out this slide. So you're going to learn a little bit about some ideas, right? You're obviously going to see some practical way of using Jupyter with some visualization tools. But if you're interested in diving deeper, I want to give a couple tips, right? So one of the things that we have inside of the Ascent Python module is this very simple Jupyter widget that we use to gather and present data. And you'll see it, and I wanted to point to the source code for that. The other thing that I wanted to point out was that we have, this is really just a Docker file, right? Or a Docker image that we use that we built up over the years. And that Docker image installs Jupyter and sets up all kinds of stuff, right? So if you're interested in what we did behind the scenes to make those Jupyter images running, you can check out the Docker file, and yeah, and you can get some ideas there. Another thing that I won't talk about, this is the thing that's like magic, and it's kind of hard to distill, even though we could do a live demo of it, is we've done some work with connecting simulation codes directly to Jupyter through Ascent. The reason why this is hard is because we do things like we use Ascent to connect a simulation code to Jupyter, and then we use Ascent inside of that Jupyter notebook and render and do all kinds of things. And it's a bit like magic. But if you're interested in this, the way to think about the capability, it takes some time to get set up on your HPC systems, is you have a simulation code that uses Ascent. You don't have to know anything about Jupyter or Python or anything like that. You can have a way to connect directly to your simulation code and get some of that data out in a Jupyter notebook. So it's pretty cool, but it's complicated. So the link to the paper we had a few years for that is there as well. All right, like the visit tutorial, here's where we live. So we're part of the Alpine project, so we're in the Alpine DAV GitHub. We have a website there, ascent-dav.org. And myself and Nicole are the primary developers on Ascent. What is it? I've alluded to it, but let's talk a little bit more. So it's meant to be a flyweight in situ visualization library, right? So something that you say, hey, I'd like for you to make some pictures for me while you're running your simulation code, something that's easy to connect your mesh-based data to. And it's really designed to take advantage of our new, our new HPC platforms that use GPUs, right? So it's never going to have the long tail of features that something like Visit or ParaView have, but it has a lot of features. I'll cover a couple of them. Importantly, it supports C, C++, Python, and Fortran. So if you have a simulation code using any of those languages, we have ways that you can connect your data in. And again, it's focused on using GPUs. It also has to use MPI, but it's a lot smaller software than some of these other bigger things. So things are already complicated enough when it comes to our new HPC platforms with the programming models and all kinds of stuff. We also wanted to make sure that we had a tool that didn't have X11 dependencies and on all of these other things. So that's one of the key things that Ascent targets. So if you want to build it, we have scripts that can help you build it, just like we have scripts that can help you visit. We also use SPAC, so same story there. One of the things about an in situ visualization tool like this, is, typically you're building it with your compilers and you're building it with your, the settings that you like. Whereas something like Visit or Paraview, usually there's a system install built with a compiler. So it's a little bit of a more intimate coupling. That's why we want to make sure it's easy for people to build using their tool sets. All right, so Ascent itself is ready for common things. So you'll see the menu up here. It looks very familiar to a lot of the stuff I talked about in Visit. Underneath the hood, Ascent uses VTKM. So remember, VTKM is that layer that allows us to take advantage of different types of GPUs. They write the code once and it can run on AMD or it can run on NVIDIA GPUs. We also use MFEM, which is a high order modular finite element library. And we have something inside of Ascent called DevilRay, which is a high order volume rendering library or a rendering library that does direct rendering on high order meshes. What does that mean? So typically when we're dealing with high order, we'll refine, right? So we'll refine to linear elements. We'll do a whole bunch of subdivisions. But with ray tracing, it's nice. We can send a ray through and we can evaluate the high order, finite element stuff. And if it hits the ray, we can just get the answer directly. So that saves a lot of memory, right? It also saves a lot of compute because you're not doing all this subdivision. So DevilRay provides that for MFEM data. You can do this direct volume rendering and direct ray tracing, which is cool. Everything in Ascent is also ray tracing based. It doesn't use rasterization stuff like OpenGL. So everything is ray tracing in Ascent. So pictures are good, but like we said, some of the most exciting things you'll see people, or exciting times you'll see people have are with curves. So we got to be able to get curves out, right? So Ascent also has some good stuff for doing analysis, including some derived field support like Visit, time histories, things of that nature. One of the really interesting things that Ascent provides that also we've been doing a lot of research on are triggers. So again, if you're going to use in situ, you might be scared that you're going to miss something exciting happening because you don't get to steer it. Triggers are a way to mitigate that. You can set up conditionals. So like ideally, if something exciting happens, I'd like 30 pictures, right? Or if something exciting happens, I'd like to export all my data, right, to make sure I don't miss it. So the trigger infrastructure that Ascent has is really cool, and it supports that. It also supports, even though it's an in situ tool, it supports bridging to other things like files. So HDF5 files are very important. We can drop right into Python. I'm going to be using it in Python now, so that might seem weird, but if you were on a Fortran code, you could drop right into Python, right? Another cool thing we have are scalar images. So again, you're scared about the choices that you have to make a priori. One of the most important choices you can make is like which color table to use, right? Well, if you do a ray trace and you save out the floating point values of that surface as opposed to a color table, then you can go back and apply different color tables and do a better job. So that's what scalar images are all about. And of course, Jupyter. A couple things I want to highlight. This one is related to Jupyter. So again, the WarpX folks, when we're working with them, they wanted to iterate on how they wanted to set up their plots. So they use their Docker image on a very small run, and they kind of iterated that, and they developed some actions that they could use on bigger runs. So that was fun. Another one, this is from a while ago, but this just demonstrates how far up we've been able to scale Ascent. So when the Sierra system at Livermore was being accepted, Sierra's the little sister to Sierra's the little sister to Summit at Oak Ridge, right? We were able to run on the full machine in situ with the simulation code. Simulation code was running the GPUs. We were running the GPUs. It was really exciting. We did ISO surfaces and things like that, running on 16,000 GPUs. We're hoping very soon to run on, Frontier, and then eventually Aurora. So we're getting excited about this stuff. We're going to have some new slides here hopefully soon. So with Ascent, all the installs that you have all these examples in them. I'm going to just give you access to a notebook, so you'll have that. But all of our installs have this. I'm focusing on Python, but they're also C++ examples. All right, quickly before we get started, just tell you a little bit about Ascent. There's 5 methods in Ascent that you have to learn. So open and close are pretty simple. Open, you might pass it an MPI communicator. Close just closes things down. Publish is how you get your data in. Execute is where you ask Ascent what to do, and you say, please give me these things. And then info is something that tells you about what happened last. So the last execute, I did all these things. So you're saying, how can we get away with 5 methods for the whole interface? And that's the trick. The trick is that we use Conduit. So Conduit is this in-memory description library that we developed at Livermore. It's a multi-language thing. I'm going to talk a little bit more, but it makes it so that our interface just takes conduit trees and everything plumbs through that. So what's Conduit? So Conduit's something that we started a while back. It was something that we identified. There were a lot of hard things with sharing between all kinds of APIs in memory. So we wanted to make something that would simplify all that. So that's what we built. We built this tool. So it's based on this hierarchical structure. So you put paths in, you'll see exactly what it is and what that means when we do examples. The best way I can describe it to people in a few words is it's kind of like JSON crossed with NumPy. You think about these named trees and then leaves hang off the end. And the leaves they're described so you understand exactly everything about them in memory. So we have this nice fancy tree thing that can hold anything. On top of that, we build conventions for exchanging more complicated things like meshes. So there are rules, right? Every file format has rules about what a mesh is. So Conduit has that, and it has that for this in-memory context and also for files. We call it the mesh blueprint or the Conduit blueprint, as you've heard. And it's used for Ascent. It's also used for the new Catalyst interface. Once we have the descriptions of these trees, we can do I/O stuff a lot easier. We've got a tree described to and from HDF5, super easy. You want to ship things with MPI? Great. We know it. We know it all. We can make choices to optimize things, or we can make cases where we can't optimize things still possible. So it's a pretty cool tool. And Ascent uses Conduit for everything, so you can think of it that way. Other than the real data models like VTKM that it uses to do ray tracing, a lot of the plumbing in Ascent is Conduit. So we hand meshes through it. The fact that Conduit supports C, C++, and Fortran allows us to have these APIs. We use it for, you'll see where we can say, might have little YAML descriptions and say, please do this. We use Conduit for that. And an important feature that Conduit has is zero copy for in situ. So if you're running in situ and you have your simulation, they've already allocated all their arrays. If possible, you'd like to just point to where they already exist and describe them. You don't want to have to copy them all over to use a tool, because that could hit you with some memory threshold. So Conduit supports that. It also supports mixing things that are zero copied and not in a pretty easy way. Even if you can't zero copy everything, you can do what you can. If you go to ascent-dav.org/tutorial, which you'll see shortly, you'll see a page like this. You click that button once, you should get your own server, and then you'll be able to click through. I don't want to steal any of them, but try it, and then again, the password is learn, lowercase learn. Is it working for folks? Good? Okay, thanks for the patience. We had a little extra time, so I appreciate it. So now you can do things and you can break things just like I'm going to, right along my side, right? So here's our Jupyter notebook, our Jupyter, it's a Jupyter Hub, and we're going to look at a bunch of different Jupyter notebooks. So the first one just shows the very basic use case of Ascent. I'm going to go through that. I'm going to go through the Conduit one. I'm going to show you the blueprint ones, the mesh blueprint ones, because I think that's useful not just for this, but also for things like Catalyst. And then depending on how it goes, we'll probably do the scenes and the pipelines, just to give you an idea. So let me get this set up a little bit better here to utilize the screen better. Okay, so again, these are all Python. C++ looks very similar because Conduit makes it similar. If you don't believe me, we can argue about it later, but I can show you the C++ examples, but Python's nice now. So what we're going to do, we're going to import Conduit, which has a Python module, the blueprint module, which helps us verify things like meshes, and we're going to import Ascent. So in your notebook, you hit Shift-Enter to execute. We cheat immediately, and we use one of the built-in examples that Conduit provides us for a mesh. There's my lovely mesh I call Braid that has this interesting pattern on it. So we're going to generate that. This serves as example data for lots of things that we do. These happen to be unstructured hexes. So now we have some data, and now we're going to run Ascent. So again, Ascent only has a couple different methods. So first we open. In the notebook context, we're going to tell it we'd like exceptions to actually bubble up. When you're running and when you're running in situ, you might not like that. Sometimes you might just like ascent to, even if everything was wrong, just keep going because you don't want to crash your ascent code or your simulation code, right? So you have options like that. We publish the mesh, and we'll talk a little bit more what's in that mesh later. And then we set up some actions that we'd like to execute. Really what we're doing here, and when we talk about conduit more, it'll make sense, but we're just setting up these little trees with context, and we're presenting those all to Ascent. So the best way to think of this is not what you're seeing here, but what you'll see right here when I run it, this toYAML. So the YAML representation of what we're asking it to do. So let me run that. So here's what we did. Here's what we effectively asked Ascent. We said, please add a scene. Some of these things are like keywords, and some of them you have control to name yourself, like scene, add scene, accept scenes, and then we have S1 and P1, which are our names. We want to create a pseudo color plot of this field braid, which we happen to know exists, and we want to make a picture. Save it to this file format. Now, here's where we have our Ascent widget, so this is pretty cool. So if I hit enter, what we already did before was we rendered out that PNG. That's all been done for a while. When we hit enter here, what this does is it looks at Ascent and it calls info, and it gets all the information it can about what just happened, including all the renders. There could be 10 or 20 of them that happened. There's only one here. All the renders that happened, and then also like the actions, right? And we have this nice Jupyter widget that just wraps that data and presents it back to you. That's the thing I said, hey, maybe this might be interesting at the beginning. Look at the source if you're interested in how to do this. And that's it. So that's an example of making one picture. This here, you can set up with as many scenes or as many plots as you want. There's also options for all kinds of camera angles and things. We'll go through a couple of that stuff. But this is just to show you the most basic example. Second notebook, let's move on to the second notebook. So this is the conduit basics. So this just tells you a little bit about how conduit works. And it's, again, the way I describe it to people, the easiest way I can say it in the fewest words is like it's like NumPy, like Python NumPy crossed with JSON. You have these different trees that you're going to build up, and you're going to pass those around either for data or to ask things through an API. So inside of Python, it does use NumPy as the ubiquitous array format, right? So we import conduit and NumPy, and at a basic level, you can think of this as like a key value thing. So I take my node, and now I have looks like a dictionary, but it's like a really fancy dictionary, and I can assign things to leaves on that dictionary. So if I say key value and I print it back to YAML, I get something like this. However, it's also hierarchical, right? So these slashes here will actually impose hierarchy in the tree. So, like a file system is just analogous to that. We have this nested nature here. So dir1, dir1, dir2, val, and if I look at it now, I actually have this tree of information. The other really important thing about this, so the hierarchy is important. The other really important thing is this zero copy nature. So first I'm going to show you how to put some values in there, and then I'm going to show you how to zero copy values in the tree. So in this case, we just do a Fibonacci sequence. So that's for the first few things. So that's pretty simple. You notice we're using set. So set means copy that into conduit. And then the next example, we show how to zero copy it. That is done with set external. So there's a whole bunch of methods that are related to set. It's easy in Python because you just give it NumPy arrays. In C++, it expands out to all these different types that match up with bit width styles. In this example here, we're doing the same thing twice. So we're setting Fibonacci sequence here for the deep copy and Fibonacci sequence here for the shallow copy. But after the fact, we go in and we change some values in the original arrays. And you'll see for the shallow copy or the external, there's a lot of ways to call this. You'll see that is impacted in the conduit representation, which when we convert it back to YAML, it happens. So here we go. So we got our tree, and our tree is telling us the deep copy, those are the values, and the shallow copy, here we go. We twiddled that to -1 there, and it's impacted. When you're running a simulation code, you want to use set external for your fields that you're passing, right? In some cases, codes can just set their conduit tree up once, and then they're done. But if you change a whole bunch of stuff, if you deallocate things, it's not magic. So luckily, you can always copy it in if you need to. All right, any questions about conduit trees? We're gonna see some more of them. We're good? Okay, so let's move on to the third example here. So this is the mesh blueprint examples. So you saw that I can do whatever I want with that tree. I can put whatever keys to my heart's desire in there. That's great. If I use a whole bunch of keys that no one else understands, it's not going to be useful, right? So we built on top of it this blueprint concept, so we can share rules. You know, what's a mesh? Well, we have expectations about what's a mesh. So the tree itself is dynamic and it uses arrays it leaves, but then we build this higher level context using something called the blueprint. So this shows you some examples of creating mesh data with the blueprint. Again, this is the thing that if you're running a simulation code, you kind of do once, you get this figured out, or if you're using MFIM or AMRX, you already have these type of wrappers so you can use them. All right, let's get going. All right, so here's an example. The first example is a uniform grid with a field on it. So the way you think about these things is that there's, there's ways to specify some things implicitly with a rule, and then there's ways to specify things explicitly, like with unstructured grids, right? But for a uniform grid, we're using a little recipe where we say, oh, I have 100 by 100 by 100 points in space, and they have this dx, y, and z. And then Ascent can look and say, I understand that. I can figure out that that's a uniform grid, right? So that's what we're doing here. We're building up a set of coordinates in space. So we define those in terms of their logical dimensions, I, J, K. So that would be 9 by 9 by 9. And then where they're anchored in space, so their origin, X, Y, Z. And then a dx, dy, dz. And so those are just points in space, but we also have to understand a topology, so how they're actually glued together. So in this case, we can just infer that from the coordinate set. Since the coordinates are implicit, we can infer that the topology is implicit, and everything's great. One thing that we do in Blueprint is we link things by names, right? This allows us to actually we could have 30 chord sets in here if we wanted to, and 30 topologies in here. So in this case, you'll notice that we have chord set chords, and the topology here called topo, we link them together. And with that, we can kind of loosely couple the different parts of the tree and build up a validation step for all this stuff. The other thing we add in this example is a field. So fields are important. If you just have a mesh, remember our aneurysm thing earlier, we just look at the mesh, it was pretty boring, but the fields are where all the action was happening there. So in this case, we have fields and we associate that with the topology. So this is really simple. This just sets up a field here that goes 0, 1, alternating for every element, or every vertex, sorry. It's associated with the vertices. And fantastic. And then for to show off, we use set external here. That's fine. Great, so we created this mesh. Here's what it looks like. We can always convert things to and from YAML, which is nice for humans. If you have a billion element mesh, don't do this. Although when you print it, it wouldn't, so I did 2 YAML, but when you print it, it wouldn't print all those billions. I still don't recommend it. What do we got here? So we have the tree that we created. Again, those slashes that I used before were what allowed us to just quickly build this hierarchy. And then all the details of our coordinates are there and our topology, and then the big thing here are all the alternating values, right? These are all the values for that field. This is a runtime thing. It's a runtime thing even in C++. So we need to make sure that we didn't screw something up. So we have this mesh blueprint verify. So we call that, and it says, you've done a good job. If we didn't do a good job, okay, what's going on? Let's go ahead and not do a good job here. So let's say I need to know what type the coordinates are. If I don't, I'm going to be in trouble. That's one of the required things. But what if I had typo here instead of uniform? Okay, so let's just see. We got our typo here, uniform, right? If I run this verify, it's going to say, oh, wait a second. Something's wrong. You're presented with a similar tree that you would expect, and it tells you where things went off the rails. Hey, you're missing type. You might not obviously, you're like, no, I typed type, but whatever. It's right. You go back and say, I screwed it up. So this type of runtime validation is you can look at. You can also write scripts and things like that. This is just another conduit tree that pops out, so you can process this runtime validation. There's other stuff in here, like there's optional things. It'll note that. It'll say, hey, I saw you had this optional thing. Great. But let's go back and undo our typo. Type. Oops. All right. Okay. So now we're back to verify success. That's good. Now we're back to what we saw before. And this is a little bit less mysterious now, right? That mesh is the thing that held all the state. If you're running an MPI, each one of the MPI tasks would publish its local domains. That's a way to think about it. We needed to have better documentation to describe this, but you would be publishing, minimally each one would be publishing their own local domain through this call, and they all coordinate. In this case, we're going to make a picture just like we made before. So let's do that. Again, everything we do, we kind of show the YAML equivalent. You can actually write a YAML file if you want to, and it'll parse that on the fly. That way you don't have to compile things in if you don't have Python. You can just switch your YAML file out on the fly. And we got our picture. Fantastic. So there's our alternating thing. We just did 1, 0, 1, 0 associated with the vertices. Another example, we don't have to spend too much time on it, but I just want to point out what's different here. This is an unstructured grid with 2 tetrahedra. Unstructured grids, we provide explicit coordinates in this case. So instead of creating a recipe for how they fill space, we're saying, no, here's where they are in x, y, z. And then we're also providing explicit connectivity. So in this case, we have the 2 tets, and we say, well, these tets are these 4 points, and these tets are these 4. The second one's these 4 points, right? So this is different in how we set up the coordinates, and then this is different in how we set up the topology. There's more involved there. We put some fields on this too. They're pretty simple. We only have 2 topologies, so these just flip-flop between the 2 fields. Let's run it. Here's our mesh. So that's our hierarchical structure. We like to keep ourselves honest. Good thing. We didn't mess anything up. And then we can go ahead and make some pictures. I'm going to skip the third one. You can do it if you want to, although sometimes on the cloud servers, the little dragger that shows the time varying thing is slow because we're not paying for big processors. But this one just renders out a whole bunch of things with Ascent and then shows them like a time series. I'd rather go to these scenes examples. And let's see. Oh yeah, we have a good amount of time. So so Ascent, it's a little bit different than a tool like Visit. It's kind of declarative in the way that Dave was talking about, right? You say, hey, I'd like you to make these things for me. You're not programming it and directly tweaking all the things. You're providing this tree of the description, and then it will go and implement it for you. So in this example, we show how you can use multiple scenes. Again, it's important for you to be able to, in situ, do a lot of things at once so you can get all the views that you like. So in this example, we create 2 plots. So we have a plot of var1, which was the tetrahedron example we created before, and a plot of var2. And we do them all with 1 dispatch to Ascent. So let's run that. Oops, I got to go back to the top. Sorry. All right, so here we got our tree that's a little bit more complicated. That's effectively what we're asking Ascent to do. Please make these 2 pictures. And let's take a look. And cool thing here, so when there's multiple pictures, we can actually look at those in this little Jupyter widget. Again, it looks at the output of Ascent and it says, here's all the things I did, and it can create a summary of that. It also will always show you the actions that were done. So, so that was rendering 2 different independent pictures, but you can also render pictures together. So what's the best way to describe this? So the 2 pictures we drew before were 2 different scenes in a movie, right? And now we have 1 scene, but we're going to have multiple plots in that scene, just like Visit when we added a mesh plot and we added a pseudo-color plot at the same time. So we're going to do that here. And it's a little subtle, but there's a white line there. That's actually the mesh outline, right? So we asked it, please add this 1 scene with these 2 plots. And you see how you can combine these things, right? You can have as many scenes as you want. You have as many plots as you want in each of them, and get a whole bunch of stuff done. Camera parameters are important. So we have a default camera. For some of the things you saw before, you probably wouldn't know, but they were actually 3D. So the default camera can only do so much. I'll show you a cinema example in the future because it'll do a whole bunch of different angles. But for now, this just shows how you can deviate from the default camera parameters. So here we are we are creating a render within the scene. That's another abstraction. You can set up, mesh plot and pseudocolor plot, and you can create all kinds of angles around it with a render just by changing the cameras that are used. And we have a default thing, and then you can think of it as changing different default parameters. That's usually the easiest way for a human to do it. All the parameters you can set yourself, but normally you just think about it as, well, I want to just change from the azimuth a little bit, or I want to zoom in a little bit. That gets you really far. Let's run this one. So here's what we asked it to do. And here's our picture. So we moved it, and then we actually did 2 of these. The other one was just zoomed. It wasn't rotated and zoomed, but that just gives you an example there. Color tables are important too. Let me go on to, so I'll run this one real quick. So we have a bunch of built-in color tables. They're documented. There's a link in there. But you can change that, and you're going to obviously change things like the limits as well. In this case, I think the Inferno color table is a very bad choice with a black background because the 0 is black, so it makes it look like there's nothing there, but we have to make better choices. All right. This I'm going to do quickly, and then I'm going to show some extracts. So this is like visit, like doing operators. You could add a whole bunch of filters in a pipeline, so isosurfaces, slices, all that stuff. So let's do some examples here. First example, we do a contour. So in the contour, we're saying we'd like it to be on the braid field, which it happens to live on our data set, and we want it in these 2 places. And then we render that scene with the output of our pipeline. So this is important. Sorry, I went too fast. So we add a pipeline. A pipeline allows us to transform data. If we don't add a pipeline, whatever data came in is just going to be used. So you published a mesh. If you add a scene, fine. Well, whatever you publish, we're going to use. These pipelines have names. You can name them yourself. We uncreatively called it PL1 for pipeline 1. But when we go to render it down here, we link those names up, just like we link things up in the blueprint. So this tells us, hey, I would actually like to render my scene with that pipeline. Again, there's flexibility here. Say you might want to render the input data. You might want to not even render your pipeline data. You might want to just save it out. You don't have to make a picture of something that you've made a contour of. You could just save it out if you want to. So let's take a look at this. 2 things we asked it to do. Please add this pipeline. Please render the result of that pipeline. And here's our picture here. So there's our contours of braid. You can maybe see why it's called braid now. The order in which you add things, if you add multiple filters, is applied here. So here we do a clip and then, or a threshold and then a clip. So this is a complicated example. The details don't really matter. Just we're doing 2 separate filtering operations, right? And then we get this example here. So what it was doing is it was doing a threshold. Threshold just rips elements out of the problem if they don't match a criteria, so that's why you get this Legos-like look. And then it was also doing a spherical clip, so it like spherically voided out that center there. Multiple pipelines I am going to skip, and I'm instead going to look at some extract stuff. So we want to do things in situ. We can't get away with not having files forever, right? You do want to save things. In particular, though, what you might want to do is if you have a whole bunch of slices that are really important to you, you'd like to calculate those in situ, and you'd like to save those off, and then come back and just read those teeny data sets as opposed to your giant data set, right? So in Ascent, we use something called extracts as the escape hatch to get outside of the code, and you can pick up stuff somewhere else to use it. So in this example, we show how to save blueprint HDF5 files. So you can actually save those directly with Conduit, but if you're doing something like a isosurface or something like that, you want to turn around that and save to blueprint. You're not going to be able to do all that with Conduit. You need something like Ascent. So we're going to show that, and I'm also going to show Cinema, because I think that's actually a very interesting way to think about this. So let's run these examples on 6. I'm in 6 now, sorry. All right, relay extract example 1. So before we added pipelines and we added scenes. In this case, we're doing neither. We're just adding an extract. So we're saying, hey, please have this extract. The names are a little bit weird. We should probably just tune it up because everyone just thinks about it as blueprint. We should just have it be called the blueprint extract and at the end of the day, that would be great. But this is the current syntax for it. Please use relay, which is what Conduit uses to save things out, and please save it to a blueprint HDF5 file. We run this, and I mean, we don't get a picture, so because we're not asking it to render a picture, but it tells us, hey, here's your file. I wrote out this HDF5 file, and that HDF5 file does exist. If you weren't running in the cloud and you had Visit, you could just turn around and open this up with Visit, but you don't have Visit there. So this is just to show that it does exist. Again, you can combine pipelines with extracts, or you can actually, this example just shows you, hey, I only want to save one field. Maybe the data that you're publishing is huge. Maybe it has all these chemical species in it, and all you care about is saving out pressure. And you're like, I don't want to have huge HDF5 files with hundreds of chemical species. Just save out pressure. You can do that, and SimCodes have used this as their own like graphics dump capability. So what we do here is we just ask only for the field braid by name, and we get that. And you can also do contours, right, and things like that. And the data that you compute, that's what will be saved, not the entire data. Let's finish off with the cinema extract example. So Silvio talked about cinema. The idea here is, again, we're trying to make people more comfortable with in situ. You have these trade-offs. If you can't pick your camera angle, you might be really sad. So what cinema does is it says, well, let's not worry about that. Let's use a whole bunch of different camera angles, and let's just render a whole bunch of images. And then we have an image database that we can kind of interactively use, almost like we were using a regular viz tool, but it's a lot smaller than the full data set. So in Ascent, this cinema thing is actually an option in our rendering. So we set up things, so we say, hey, this render is going to be a cinema render, and we tell it a number of angles that we'd like to use. So we want 5 angles in phi and 5 in theta. And then we say, please look at please save this to a place. So cinema actually will write out like a web page that has all these images linked in. But we can also look at it in the Jupyter notebook. So let's run this. It takes a little bit more time because it's going to actually have to render a whole bunch of pictures. So here it goes. And then if I look at it in this normal viewer, you can just get like kind of a whole bunch of random angles and stuff. But luckily, there's this cinema, this cinema viewer that they provide a Jupyter widget for. We can use that. Let me make it bigger. And then they have the sliders for you to do like phi and theta, right? So you can tell which way one of the rotations was. We don't have a time series here, but if we had a time series, then we can slide this. So this gives you, in some versions of the web page, you can actually click and drag it, and it feels like almost real. But this gives you a pseudo-interactive way of viewing this because we rendered out that image database. Another thing we can do is we can run Python directly inside of Ascent. Be a little bit weird to do it here because we're already running Python, but imagine you had a Fortran code or a C++ code and you said, I want to write a Python script to do that. So because the conduit stuff binds through all these languages, all the data that you've presented to conduit just can show up in Python. Ascent can bring that Python to the table for you, I guess is the way to think about it. So this example just shows that, and it proves that we calculate the same thing in Python that we calculate in another Python. I think that's where I'm going to stop. Again, so thanks for learning about Ascent and also for some of this Jupyter stuff. There's a couple examples in there if you're interested in doing your own Jupyter things. The Ascent widgets, even the cinema widgets, right, give you an idea of some ways to connect some of these pieces. And and then there's some other examples we can play with. I will eventually tear them down. And thanks for your patience earlier. I appreciate it. So questions, I guess we can.
That's maybe a question to what the previous talk that you gave, but just like your intuition, Visit and Parallel seem to me very similar, like offer similar functionality and also similar interface. Do you see any pros and cons for either of them?
Yeah, so they're both big tools. Of course, I'm not an expert ParaView user. You might have guessed that. They have different user communities, right? I think one of the things to think about in terms of whether you would use one tool or another is people have different preferences and different like different things, right? Some of the visit stuff, again, was forged with the computational physicists at Livermore. So if your brain works like a Livermore computational physicist, then maybe you should think about using visit. It also gives you rights to beat down a door. But I mean, they both leverage some of the same infrastructure like VTK and VTKM. They differ in some of the parallel infrastructure that's presented to them. So they've emphasized different features in the past. ParaView has some really nice, physically based rendering things that like Visit doesn't have, and more connections with some of the vendor-specific rendering tools for that. We've invested a little bit less in that. They both have scaled up gigantically over the past 20 years, so I think they're both pretty scalable. So I think they're both great tools. So I can't tell you, the head-to-head will have to happen in your head, I think. But there's certainly, as a daily driver of these things, you use the one that you like the best. Yeah. Yes.
In your earliest example, you highlighted these numpys that people get and all that. I'm curious if the interoperability with Ascent and CuPy and getting that on GPUs, and if that's useful in some cases and how that can be.
Yeah, so we haven't tried that, but it's certainly possible. So so we do things like that in C++, where people have given us pointers that are already on a GPU, and we can use them sometimes. I think there would have to be infrastructure for CuPy to make that work, though. It's not magic, right? But it's certainly something we could explore. The goal is to do this zero copy stuff. And if it's possible to go all the way from C++ to a CuPy zero copy, we could probably make that happen, right? It's just describing where it is in memory. So ideally, we'd want to do something like that. If you had a simulation code that was using CuPy to write, we would like to do something like that. Yeah. Is that a good enough answer? Or? Sure. Yeah. Questions, quandaries? The notebooks did work for people? Okay, good. Good. Yes?
Yeah. All the visualizations in the notebooks seem to be only 2D. Is there a way to make them 3D so that you can interact?
Yeah. So yeah, what you're seeing at the result is PNG files, effectively. With the other Jupyter stuff that we talked about, this interactive thing, we did have a way where we could have like a widget where you could click and turn, and then it's still rendering out PNGs and sending them back, kind of like what Visit or ParaView did. And so the answer is sort of. I mean, it's still a little clunky, and we'd like to make it better. So it doesn't ever feel good as a Visit or a ParaView, I guess I would say right now. It could still be made better though. And deployment's a little bit more complicated too, but yeah, it's possible to do it with more investment. Yeah. Yes?
So with this in situ visualization, so you discussed that there's some cost overhead that comes with the visualization part of it. Have you thought about, or have you considered the possibility of allocating separate nodes for visualization, and just not using the compute nodes for just computing these things? Although there will be some memory overhead to copy things there or to access things, but yeah.
Yeah, we have. I had this question earlier today too. I mean, that's what an in-transit approach helps with, and Sensei has tools for that. Visit or Ascent also has some tools for that. I think you have to think of it in terms of trade-offs. So, if you're running a simulation code on 1,000 nodes, well, are you going to get through the job faster if you run 1,000 nodes or if you run 1,100 nodes, right? If you allocate separate things for visualization. So while you could stream it over to those, you're really using more resources. You understand what I'm saying? So you have to think about it in those terms as well. But yeah, there are ways to say, hey, like Ascent has a capability that we don't use that often. Basically, you say, hey, Ascent, send this to some other MPI task Ascent, and then you just run your visualization on a subset of the stuff there, and it works. For users, it's complicated. That's my honest answer, right? Because they're not used to launching multi-MPI jobs, and when something goes wrong, they're like, ah. So this tightly coupled in situ visualization is just the easiest thing for people to wrap their minds around, And yeah, even in an in-transit case where you have another MPI task that's multi-launched, if the visualization crashes, you're still in trouble. Although there's other transports that do a better job of that. But I think it would be, it's a really cool idea, and it would be something that we'd love users who can take, who are excited about that to play with that. I think that's the way I would say it, but it's certainly possible.
Thanks.
And to add to that, from the facility perspective, right, I think sort of changing the mindset a little bit of, I'm not just budgeting for my simulation, but I'm budgeting for my analysis at the same time, right? And so, like Cyrus said, don't plan for 1,000, plan for 1,100, whatever the right fraction is. Or to do it directly on the nose and do blocking, but factor in the fact that you're not just simulating, you're also doing the analysis too.
For like a really large job, sometimes we do add on more nodes because sometimes what happens, especially with NAS supercomputer, is that the nodes fail and then they have to restart the node. So you have this, so basically you try to reserve more nodes than you actually need. So I guess we could use Dart nodes for visualization if they have enough memory, obviously, for storing the data.
And there's all kinds of ways you could do this. You don't have to tightly couple it with MPI, right? You could have something writing out to RAM disk and then maybe have things on the same node, or writing out to a burst buffer file system and then have another job that just kind of watches. There's a lot of possibilities. It's just getting the complexity to a place where people will want to do it every day is a challenge. Thanks everybody, and thanks for your patience earlier. I appreciate it.